Hi friends, today we will study some topics of power system protection. Let us begin with the question why power system protection is required. As we have studied in the chapter of fault analysis that the magnitude of fault current is very high. The magnitude of fault current is much higher than the magnitude of normal current. And such a high magnitude of fault current may be dangerous for power system equipments like generator, transformers, transmission line or feeders. So it is necessary to provide protection for those power system equipments. Let me draw the single line diagram of a power system, simple power system. Let's say here we have generator, this is bus, here we will have a step up transformer, transmission line, then a step down transformer, and here we will have load. We have to provide protection for, let's say this is bus, we must have protection for bus, transformer, this is generator, this is load bus, this is again transformer. So how can we provide protection for these equipments? The one way of providing protection is use of fuses. The appliances in our house are protected with the help of fuse. But there are certain disadvantages in case of fuse. The one disadvantage is that after functioning, let's say a fault has occurred. Let's say here we have fuse. Let's say a fault has occurred here. So due to high value of current, how fuse will operate? Due to the high value of current in the wire of fuse, this wire melts and it gets disconnected. So to get back the line into function, you will have to replace this fuse, or we can say that after functioning, fuse gets damaged and you need to replace it. So it needs to be manually replaced. It is not automatic. So in power system protection, instead of fuse, circuit breakers are used. Circuit breakers are a kind of automatic switch. Instead of fuse, we will have a circuit breaker here. These are automatic switch, that is, when a fault will occur, it will open its connection or the circuit breaker will open. And when after some time, when the fault is cleared, this will automatically close its connection. So it will resume the supply of electricity. While in case of fuse, after functioning, fuse gets damaged and it has to be manually replaced. So circuit breaker can be remotely operated. So the one component that we will study in power system protection is circuit breakers. Okay, circuit breakers are only switches. These are automatic switch, but how this circuit breaker will operate it, or who will make the decision to operate the circuit breaker? The decision of operation of circuit breaker, this is even the decision of operation of circuit breaker is not manual. Decision is also automatic, and the decision is taken by relay. Whenever a fault occurs, the magnitude of high current, the magnitude of current becomes high, and this is sensed by relay. So whenever fault will occur, this will be sensed by relay, and it will send command to circuit breaker to open its connection. Apart from circuit breaker and relay, we have to study current transformer and potential transformer or voltage transformer. These two are in instrument transformer. We have already studied instrument transformer in measuring instruments. So what is the use of instrument transformer here? The use of instrument transformer is, the first use is to provide electrical isolation of relay from line. As I said earlier, the function of relay is to sense the fault. And how the fault can be sensed? Relay can sense the magnitude of current in the line. If the magnitude of current is much higher than the normal current, it will sense the fault. But relay is not going to sense the current directly in the line, okay, because the magnitude of normal current is very high. The magnitude of even normal current is very high. Let's say it is 100 ampere, and in case of fault it may be as much as 500 ampere or 600 ampere or even higher. So relay is not going to sense these currents. Instead of this, we use a current transformer. Let's say here we have a current transformer, okay. So the first use is to provide electrical isolation of relay from the line, and second is reduce the magnitude of current that operates the relay. Let's say the turn ratio of the current transformer is, let's say this is of 500:5. So the current of 100 ampere, let's say 100 ampere current is a normal current or rated current. So corresponding to 100 ampere current, the current that will enter into the relay will be, the ratio is 500:5. So the 100 ampere means current in the secondary of instrument transformer, or current in the secondary of current transformer will be 1 ampere. So 1 ampere current will be corresponding to normal current, because 1 ampere current is corresponding to 100 ampere and 100 ampere is normal current. So if 1 ampere current enters into the relay, it will treat it as normal current. Let's say 500 is fault current. So 500 current, this will be a 5 ampere current in current transformer. This will be treated as fault current, okay. So with the help of current transformer, the relay will not have to deal with 100 ampere or 500 ampere. Instead, it is dealing with 1 ampere and 5 ampere. Similarly, in many cases, in many relay requires the bus voltages. So this is the bus voltage. Here we can use potential transformer. So even this instrument is providing electrical isolation from the line or the bus, okay. So these are the three basic components that we will have to study in power system protection. Out of these three elements, we have studied principle of, or the operation of, current transformer and potential transformer in measuring instrument. So basically we have to study circuit breaker and relay. If we talk about the questions that come in the examination, those are mostly based on relays. Relays are of basically three types of relay we have to study. Those are in syllabus of GATE: overcurrent relay, impedance relay, differential relay. Apart from these three relay, we will study directional relay. Directional relay we will study immediately after overcurrent relay. So let us begin with overcurrent relay. As the name suggests, the overcurrent relay will be based on the fact that in case of fault, the current is much higher than the normal current. So in case of overcurrent relay, there will be a reference current up to which the current will be treated as normal current. But as the current exceeds this reference current, that current will be treated as fault current or abnormal current. So if we will say that if the line current is less than reference current, the reference current of the relay This can be set manually. This current will be normal current, and if the line current is greater than reference current, this will be treated as fault current. And for this condition, operation of relay can be started. Maybe started. The reference current is also termed as the pickup current. And the overcurrent relay finds mostly its use in radial distribution system. In case of radial distribution system, there will be many feeders which comes radially outward from the source. I am drawing only one feeder here. So this is a feeder line, this is source. The feeder is coming radially out from the source, and it will feed to the primary of distribution transformer, or we can directly represent load here. This will go to load. Let's say this is bus A, this is bus B, this is generator bus, and this I have drawn for, let's say this is relay 1 and relay 2 along with its circuit breaker. Let's say we have R1 and R2 are overcurrent relays. So for this system, there will be some normal value of bus current, and accordingly we will have normal value of feeder current. Here we will have normal current. Let's say the normal current here is 50 ampere. Here also normal current is 50 ampere. But in case of fault, the current will be much greater than 50 ampere. Let's say a fault has occurred at this point. So how this fault will be cleared? If a fault occurs at this point, the amount of current here will be very high. So that amount of fault current, this fault current will pass through relay 1 and hence sensed by relay 1. Okay, so we can say that IF current, IF will be seen by relay 1. Okay, whatever fault current is passing through R1, the same current may pass through R2 also if relay 1 does not operate. In the most favorable condition, what will happen? After the fault, we will want the relay 1 to operate, and this will operate the circuit breaker, and this will be open circuited, and this part will be isolated from the system. And here this load will not be interrupted. This load will continue to take power supply from the source. Okay. So here we will say, for this fault, R1 will provide primary protection. For fault at bus A, let's say this is near bus A. So we will say that for fault at bus A, R1 will provide primary protection. Let's say R1 provides primary protection for fault between bus A and B. But let us suppose a condition when this relay R1 fails to operate. So this fault current will continue to flow through this path. This relay will not operate. Okay, so if this relay will not operate, the same fault current will flow through R2. So we can say that if any fault occurs between A and B, this fault current will be seen by both relay R1 and R2. We will say that IF will be seen by both R1 and R2. And if relay R1 fails to operate, in that case we will want R2 to operate. So we will say that R2 provides remote backup protection for fault between A and B. Okay, now consider a fault between bus B and let's say this is bus C. Let's say a fault occurs at this point. So for this fault, this is relay 1, this is relay 2. If fault occurs at this point, the fault current will flow like this. Okay, so this fault current will not be seen by relay R1. Okay, this fault current will only pass through R2. Okay, that will provide primary protection. We will say that R2 will provide primary protection for fault between B and C, and there is no remote protection for this fault. Okay, we'll say that for fault between C and B, R2 provides primary protection. There is no backup protection for this fault. Now coming back to fault between bus B and A. Let's say fault has occurred at this point, and consider the time when the fault is not cleared. So the fault current will flow like this. Okay. In this case, R1 as well as R2 may provide protection. If the relay R1 operates, this part of the circuit will be isolated, and this load, the load connected to bus B, will still be getting power supply from the source. So this will be the desirable protection. But if this fails to protect, in that case the relay R2 will be operated, and in that case this whole part will be cut off from the electrical supply. So for this kind of fault, the desirable protection will be provided by relay R1. We want that for this fault R1 to be operated, and if R1 fails to operate, in that condition only R2 should be operated. Okay, R2 should be operated only when relay R1 fails to operate. So to achieve this condition, the operating time of R2 must be greater than the operating time of R1, at least for this fault. Okay, we will say that a fault between B and A, the operating time of relay R2 must be greater than the operating time of relay R1. Okay, so since I said operating time, so we will first study the factors on which, or the features on which the operating time will depend. Operating time of relay. As I said earlier, for each relay we can set its reference current or the pickup current. If the actual current is greater than pickup current, this will be treated as a fault current. So let's say I current is flowing here. Okay, the ratio I by I pickup or I reference this ratio will give an idea about how much current is flowing in the line. If this ratio is greater than 1, this will be corresponding to a fault current. If this is much greater than 1, or if this value is higher, we will say that fault is severe. If this value is less than 1, we will say that this is the case of normal current. Okay, and this ratio is called plug setting multiplier. Okay, if this ratio is high, it means the fault current in the line is high. So in this condition, what we will want? In this condition, we will want the relay to operate faster. Second is time delayed definite time relay. And the third is, which is mostly used, inverse definite minimum time relay. The first is instantaneous relay. As the name suggests, what this relay will do, as soon as it will detect any fault, it will operate. In this relay, there is no intentional delay. In instantaneous relay, there is no intentional delay. There is no intentional delay. In time delayed definite time relay, there is a definite delay, normally of 0.3 second, after which it operates. There may be a question, why to provide a delay? The relay should always operate instantaneously. But looking at this example, consider the fault at this point. What we want this relay to operate. The desired operation is operation of relay first. Because if for this fault R2 will operate, it will unnecessarily isolate this part from the system or this part from the electrical supply. So what we want, for this fault, we will provide a delay to this relay. Okay, let's say 0.3 second. So the relay R2 will wait for relay 1 not to operate. If this relay will operate, it will isolate this part of the circuit. If this will not operate, then R2 will operate. So this is the use of providing delay in the relay. So in case of time definite time relay, time delayed definite time relay, the delay is fixed, that is 0.3 second. The R2 will wait for relay 1 to operate first. If relay 1 fails to operate, R2 will operate. The third is inverse definite minimum time relay. This relay I was talking about. In this type of relay, time of operation has inverse relation with plug setting multiplier, that is the ratio between current, the fault current, divided by the reference current or the pickup current. If this ratio is high, the time of operation will be less. So for this type of relay, on x-axis, let's say we have plug setting multiplier, and here we have time of operation. We will get this kind of curve. This is for inverse definite minimum time relay. And how will be the graph of time delayed definite time relay? It has nothing to do with this ratio. If there is a fault, the delay or the time of operation will be fixed. This is 0.3 seconds. But this type of characteristic is used in relay coordination. The relay coordination that I discussed here. This third type of relay, it has further 3 types. Depending upon how fast the time of operation decreases with PSM, plug setting multiplier. Let's say this curve represent a standard inverse relation. Okay, the time of operation has a standard inverse relation with the plug setting multiplier. In the second graph, the time of operation reduces at a faster rate with PSM. So for this graph, we will say it has a very inverse relation with PSM. And for high value of PSM, the time of operation becomes nearly constant. For low value of PSM, it has inverse relation. The time of operation has inverse relation with PSM, and for high value of PSM, the time of operation, the delay in the time of operation becomes constant. And in this graph, it has extreme inverse relation. Okay, coming back to our problem of radial distribution system, that if a fault occurs between A and B, how to ensure that first R1 relay will operate, and if R1 fails to operate, R2 will operate. Let's say in both the relay we have inverse time. Let's say at both the places we have inverse definite minimum time relay. If we plot the graph, from both the relay, same fault current is passing. Okay, so fault current divided by reference current. This is PSM, plug setting multiplier. Okay, so if reference current is same for both the relay, the value of PSM will be same. Okay, so the delay in the operation of both the relay will be same. Okay, if this relay works first, then it's okay, but if R2 relay works first, this part will unnecessarily be isolated from electrical supply. But as I said earlier, reference current can be set for a relay. It can be set manually. Okay, so if we will set higher I reference for relay 2, let's say we have higher I reference for relay 2. So if reference current is high, PSM if I reference 2 is greater than I reference 1, so PSM2 will be less than PSM1. So if PSM2, let's say this is PSM1, this is PSM2, PSM2. Okay, so if PSM2 is less, the operational time for relay 2 will be higher. But this option does not always provide sufficient time interval. We want a sufficient time interval between operation of relay 1 and relay 2. That interval is known as coordination time interval, CTI. Okay, normally the value of CTI is 0.3 second. Relay 2 will wait up to 0.3 second for relay 1 to operate, and if relay 1 fails, then relay 2 will operate. Okay, so as I said, setting the higher value of reference current for relay 2 is not a good option. This will not always provide a coordination time interval of 0.3 second. So we should have an additional feature to control the operation time of relay. So fortunately we have an additional feature that is known as time multiplier setting. Time multiplier setting control the delay of relay operation. Okay, if for a relay the value of time multiplier setting is high, it means delay in the operation will be high. So now we can plot graph of time of operation versus PSM. PSM is nothing but it reflects the magnitude of fault current. If magnitude of fault current is high, PSM will be high. So now we can plot the graph of time of operation versus PSM for different value of TMS, that is time multiplier setting. So for inverse definite minimum time relay, we know this graph will be like this. It has an inverse relation, and if the value of if we will increase the value of time multiplier setting, the time of operation will be increased. For higher value of PSM, the delay in the operation becomes constant. It becomes equal irrespective of the value of time multiplier setting. For high value of PSM, it does not matter what is the value of time multiplier setting, the delay in the operation will become equal. Okay. Let's say this is time multiplier setting 1, this is TMS 2, and this is TMS. For a particular value of PSM, okay, for a particular value of PSM, this is the time of operation corresponding to TMS 1. If the value of TMS is higher, the delay is higher. If the TMS is further higher, the delay is even higher. T operation 1, T operation 2, T operation 3. So we'll say T operation 3 is greater than T operation 2 is greater than T operation 1. If TMS 3 is greater than TMS 1, TMS 2 is greater than TMS 1. For the same value of PSM, if time multiplier setting is higher for a relay, then the time of operation will increase. This can also be observed. This is also a fact that for higher value of PSM, like at this point, the difference in the delay for the three graph is 0. As you will move in the left direction, let's say at this point, this is the gap. As you will move in left direction, the gap will increase. At this point, here this is the gap and this is the gap. Okay, so as you will move in the left direction, for a particular value of PSM, the gap between the delay for different value of TMS, this will increase. Okay, what I want to say is, let's say for this value of PSM, if this gap is, let's say this gap is 0.3 second, this is what we want here. Okay, we will set the different value of TMS for R2 and R1. Let's say this is corresponding to TMS for R1 and this is corresponding to TMS for R2, and let's say if this gap is 0.3 second for a particular PSM. Now if you will move in left direction, this gap will be greater than 0.3 second. So I can say that 0.3 is nothing but 0.3 second is nothing but coordination time interval. So we will say that if coordination time interval is in is achieved for higher value of PSM, it will be guaranteed or ensured assured for lower values of PSM. Okay, so from the graph we seen the dependence of time of operation on PSM and TMS, that is plug setting multiplier and time multiplier setting. The formula as per IEC, the formula for inverse relation is the time of operation for standard inverse characteristic is time multiplier setting into 0.14 divided by plug setting multiplier to power 0.02 minus 1. This is for standard inverse relation. For very inverse relation, the formula for time of operation is TMS into 13.5 divided by PSM minus 1. And for extremely inverse relation, the formula is 80 divided by PSM whole square minus 1. Now let us do a numerical problem based on the coordination between relay R1 and R2. Let's say the maximum load current at bus A is, maximum load currents are 50 and 50 ampere. Minimum fault current is, let's say for bus A is 300 ampere and for bus B is 700 ampere, and the maximum fault currents are given as, for bus A it is, let's say 700 ampere and 1400 ampere. Let's say this is 600 ampere. Minimum fault current at bus A is 300 ampere, at bus B is 600 ampere. So the maximum load current is given, minimum and maximum fault currents at bus A and bus B are given. Okay, so in this problem we have to set the reference current, because as I said earlier, the reference current is something we can choose for relay R1 and R2, reference current or pickup current. We have to choose pickup current for R1 and R2. There is another feature that we can choose time multiplier setting for R1 and R2. We have to consider fault at this point. For this kind of fault, first we should wait for R1 to operate, and if R1 fails, then R2 must operate. And for this point of fault, only R2 can operate. Okay. The formula for time of operation is time multiplier setting into 0.14 divided by PSM to power 0.02 minus 1. While calculating PSM, I have said that PSM is nothing but line current or the fault current divided by the reference current or pickup current. I did not tell anything about the current transformer, because even if you will find the fault current, actually PSM is decided by the currents in relay, and currents in relay passes through the current transformer. So even if you will use the current which entered into the relay through current transformer, so there will be some turn ratio. Okay, so the fault current in the relay that will enter, it will be divided by N, and again the pickup current, this will also get divided by N. So ultimately you will get the same ratio. So it does not matter how you are calculating PSM, either direct from the line current or from the current in the secondary of current transformer, you will get the same PSM. Okay, so let us first talk about the pickup current. Let us first talk about the pickup current of relay R1. So obviously the pickup current is the current which will be considered as fault current, or at which the operation of relay may be started. So obviously pickup current has to be greater than maximum load current, because this is not a fault current, this is a normal operation current. Although the load is maximum, but still this is a normal operational current. So the pickup current, or the current at which the function of relay can be started, this current must be greater than the maximum load current. So the normal value of pickup current, normally this is 125% of, or this should be at least 25% greater than the maximum load current. This must be at least 1.25 of the load current. Let us represent load current by IL. Okay. Actually, there is a gap between normal maximum load current and the minimum fault current. There is a huge gap between these two values. So we can set any value in between. You can choose any value of pickup current between 50 ampere to 300 ampere. But normally pickup current should be greater than 1.25 of the maximum load current. That is, the pickup current should be greater than, for this case it should be greater than 1.25 times of IL, that is 1.25 times of 50, that is 62.5 ampere. Now let's say you have the minimum fault current. So at the minimum fault current, you must want the relay must operate. So it is very sure that the pickup current must be less than 300 ampere, or the relay must start its working if the current in the line is 300 ampere, or before this only it should start. So normally the pickup current should be, it is less than 2 by 3 of the minimum fault current. Okay, that is, if current in line, if it is about 66% of minimum fault current, the relay should start its working. The relay must start its operation if the current in the line is 66% of the minimum fault current. It should not wait for the current to reach the value of minimum fault current. Even before that, it has to start its working. Okay, so this is the inequality. This is the inequality by which we can set the pickup current. Since initially I have not given what should be the value of pickup current, but in the examination you will not have to choose. Instead, a value of pickup current will be given in the question. If any value I am assuming or choosing from the range, okay, the same you will not have to do in the examination. Instead, that value will be given unless the question cannot be solved. Okay, so what should be the pickup current? The minimum value of the pickup current is, this should be 62.5, and what is 2 by 3 of minimum fault current at bus A. Okay, for this fault we have to, since this fault is at bus A, we have to consider minimum fault current at bus A. So we will use here 300 ampere. So IP should be greater than 62.5 and less than 200. Before the choosing value of IP, let us again discuss this part. IP must be less than 2 by 3 of minimum fault current. In case of minimum fault, let's say this is the inequality for pickup current. Let's say in the line minimum fault current is flowing. I is equal to IF minimum. Okay, so what will be the value of PSM? Plug setting multiplier will be the actual fault current, that is IF minimum, divided by IP, which is less than 2 by 3 of minimum fault current. So if this quantity is less than 2 by 3 of minimum fault current, PSM will be, this quantity will surely be greater than 3 by 2. Okay, IF minimum and IF minimum will be cancelled, and if this quantity is less than 2 by 3, obviously this quantity will be greater than 3 by 2. So by satisfying this inequality, what we are satisfying? We are satisfying PSM must be greater than 1.5. For electromechanical relay, starts its working when PSM is greater than 1.5. Is for electromechanical relay. Okay. So by ensuring this quality, we can ensure PSM is greater than 1.5. Okay, so we got IP in this range. So let us choose a value of IP as let us choose IP as 150 ampere for relay 1. Okay, now let us try to find out the operation time for relay 1 in case of maximum fault current. The maximum fault current is 700 ampere. Okay, so what will be PSM? PSM for relay 1 will be 700 divided by 150. This will be 4.66. Okay, and this is formula for operation time. This is for a standard inverse relation. Let us assume that relay satisfying this relation is used in this protection system. So we have the value of PSM. So the time of operation for R1 will be TMS 0.14, PSM is 4.66 to power 0.02 minus 1. Okay, now what should be the value of TMS? As I said earlier, TMS is something we can choose. Okay, so as far as this fault is concerned, we want this relay to operate as fast as possible. As fast as possible. So the time of operation should be minimum for relay 1 as far as this fault is concerned, because R1 is this R1 will provide the primary protection for this fault. Okay, so the time of operation should be minimum, so we have to choose the minimum value of time multiplier setting, and the minimum value of time multiplier setting is minimum value is 0.025. So we'll use 0.025 into, this will give you 4.47. So the time of operation is 0.11 second. Okay, the time of operation of the primary protection is 0.11 second, and the time of primary protection is also an important point which I forgot to mention earlier. The time of primary protection must be less than 1 second. So here it is 0.11 second. Okay, now let us discuss the case when this relay fails to operate. Okay, so for this fault, R2 is the only relay. When R1 fails to operate, for this fault R2 is the only relay, or R2 will provide the remote backup protection. Okay, now we'll talk about relay R2. What it does, it will provide primary protection. It provides primary protection for fault between C and B, and backup protection for fault between B and A. Now the time of operation, if we are talking about this fault, the time of operation of the primary protection is 0.11 second. Okay, and we want R2 to operate only when R1 fails to operate, and for this we will have to wait for coordination time interval, that is 0.3 second. Okay, so the total time of operation for backup protection, this should be coordination time interval plus relay operation time. Okay, this should be the expected time of operation for the backup protection. Okay, so the coordination time interval is 0.3 second and the relay operation time is 0.11 second. The operation time delay for backup protection between fault A and B should be 0.41 second. So for relay 2, for the backup protection, we already have the value of operation time. Okay. Now we have to find out the value of plug setting multiplier for relay 2 to provide backup protection. If we will have the value of plug setting multiplier, we can find out the value of time multiplier setting. So plug setting multiplier is nothing but fault current divided by pickup current. And remember, the time 0.11 second is the operation time for maximum fault current. This is for maximum fault current. For minimum fault current, the time of operation will be different. That we will calculate later. Okay. So what I am doing, I have calculated the operation time for primary protection for maximum fault current. Okay, and then I have set the coordination time interval 0.3 second. So the time of operation should be 0.41 second for remote protection. But this 0.41 second, now if I ask the question, this 0.41 second, this should be, I agree, this should be the time of remote protection, but whether this should be for minimum fault current, minimum or maximum fault current. So since I have calculated this time for maximum fault current in case of primary protection, so again I will have to consider the case of maximum fault current. So the maximum fault current here is 700 ampere. And as I said earlier, if the coordination time interval is achieved, if the coordination time interval of 0.3 second is achieved for higher value of PSM, then this coordination interval will be guaranteed for a lower value of PSM as well. Okay, so the maximum fault current is 700 ampere. Now what should be the pickup current for relay 2? Again I will write the formula. The pickup current should be 1.25 of load current and 2/3 of minimum fault current. Okay, now if we will consider this relay, there may be two cases for minimum fault current. The one minimum fault current is 600 ampere, that is for bus 2, bus B. For this bus, the minimum fault current is 600 ampere. That is, if a fault occurs at this point, the minimum fault current will be 600 ampere. Okay, and if a fault occurs at this point, the minimum fault current is 300 ampere. For this fault, if R1 fails, the only relay left is R2. So R2 has to provide protection for this fault current. So the minimum fault current for R2 will be 300 ampere because it has to provide protection for this current also. Okay, IP less than, so again we will have the same inequality, 62.5 less than IP less than Here if you will put 300 ampere, you will get 200 ampere. So again choose the value of IP as 150 ampere, the pickup current for relay 2. So again the value of PSM will be, now the PSM is 700 divided by 150, that is 4.66. So 0.41 will be equal to time multiplier setting into 0.14 divided by 4.66 to power 0.02 minus 1. From here we will get TMS as time multiplier setting for R2 as 0.091. Okay. Let me summarize what I did so far. We had this formula for calculating the operation time. I considered this fault, and for this fault this will provide, relay R1 will provide primary protection. So for this protection we will use this formula. For using this formula we have to find out the value of PSM. PSM is nothing but the fault current divided by pickup current, and for pickup current I used this inequality. After using this inequality I set the value of pickup current as 150 ampere, and I calculated the operational time for this primary protection considering the maximum fault current, that is 700 ampere. Okay. So for the maximum fault current and this value of pickup current, this relay, and as long as this fault is concerned, this relay should operate as fast as possible. So for making this relay fast I use the minimum value of TMS. So for the maximum fault current, using this value of IP, the minimum value of TMS, I got the operational time of the primary protection is 0.11 second. After that we have to consider the case when this relay fails. So when this relay fails, this relay will operate, and for this relay to operate we will have to set the coordination time, the minimum coordination time interval of 0.3 second. That is, this relay will at least 0.3 second for relay 1 to operate. Okay. So the total time of operation for relay 2 will be 0.3 plus 0.11. So we got the time of operation as 0.41 second. For calculating the PSM, again I will have to consider the maximum fault current 700 ampere. IP can be found out with this range. The minimum fault current even for this relay will be minimum of 600 and minimum of 600 and 300. So now we have the operation time of relay 1 is 0.11 second. PSM time multiplier setting we set for relay 1. For relay 1 as 0.025. Operation time of R2. This is for remote protection only. This was 0.41 second, and for this the time multiplier second of R2 we will have to set as 0.091. Okay. For remote protection of relay 2, the pickup current was 150 ampere. Okay, so this fault is over. Now let us consider about this fault. For this fault, only R2 will provide primary protection and there is no backup protection. So if this is a primary protection, the time of operation must be less than 1 second, and we have already set the value of TMS and the pickup current for relay 2. The pickup current is already set as 150 ampere and TMS is already set as 0.091. So what is left? For maximum fault current, IF max is, for this fault at bus B, the maximum fault current is 1400 ampere. Okay, so for this fault, what will be value of PSM? Plug setting multiplier, fault current divided by pickup current. This will be 9.33. So the time of operation will be T time multiplier setting into 0.14 divided by PSM to power 0.02 minus 1, that is 0.091 into 0.14 divided by 9.33 to power 0.02 minus 1. Okay, this time is 0.27 second, which is less than 1 second. Now let us calculate for minimum fault current. The time of operation for minimum fault current. So minimum fault current between for bus B is, this is 600 ampere. So plug setting multiplier will be 600 divided by the pickup current 150 ampere, that is 4. So the operational time will be TMS 0.091 into 0.14 divided by 4 to power 0.02 minus 1. This is 0.45 second. Similarly, if you have more buses, like there may be fault at this point. Let's say this is A point. So for this fault at A, R1 will provide primary protection and R2 will provide, for this fault, this will provide remote backup protection. Similarly, at fault at B, R2 will provide primary protection and R3 will provide, for fault B, R3 will provide remote backup protection. Okay, and for calculation purpose, we will first start with this end, the end which is at the far end from the source. We will start with this fault, and for this fault R1 will provide primary protection, so the TMS value of TMS will be minimum, that is 0.025. According to the minimum fault current and maximum load current, pickup current will be decided. Then with the help of maximum load current and pickup current, we will find the value of PSM. With the help of PSM, we will find the delay operational time, and once you have the relay operational time for primary protection, you will find out the relay operational time. Just add 0.3 for remote protection. So with this value, you will have time multiplier setting for R2. Now let us analyze this question on graph. Here we have operational time, and let's say here we have fault current. So first we found out the operational time of relay R1 for the fault current of the maximum fault current of bus A. Okay, the minimum fault current I took as 700 ampere. Maybe in the question I took the minimum fault current at bus A as 600 ampere, but in the calculation as I remember, and in the calculation I took a wrong value, 700 ampere, but it does not matter. In the question you change the minimum fault current at bus A as maximum fault current at bus A as 700 ampere. So for this fault current we calculated the operational time 0.11 second. So the characteristic of operational time versus PSM will be like this. For the fault current of 700 ampere, the operational delay was 0.11 second. Okay, and we know that this curve varies with time multiplier setting. So for this calculation the time multiplier setting was 0.025. Okay, and for the same fault, if R1 fails to operate, R2 must provide remote backup protection. So for the same value of fault current, the backup protection must be provided, and this time must be 0.3 second after the expected operation of relay 1. The expected operation for the remote protection must be after the expected operation 0.3 second after the expected operation of primary protection. Okay, let's say this is 0.41. let's say this axis, both the axes are non-linear axis. So here again we will have a curve, but this curve will be for different TMS. Obviously if you are changing the curve, it means the TMS is changing, and that is true. For relay 2 the value of TMS is 0.091. So just by changing the TMS we move from this point to this point. Value of pickup current and the PSM was same. Now for the calculation of operating time for primary protection at fault B, the value of TMS was same, so we have to be on this curve only, and the time of operation was as I remember, this was 0.2 second. So on this curve only we will move here such that the time of operation is 0.2 second. So this point is for primary protection, this is for remote protection by R2, this is by R1, and again this point is primary protection by R2.